All right, let's get started. I'm going to cover a couple of things today. So one thing I want to talk to you about really fast is our max and our mins. Okay. For the max and the mins. Now, local max and mins are called relative max and mins. Okay, absolute max and mins are absolute. Okay, something like that, right? You don't see, they're always called absolute. Okay. When we're thinking of, when we have our picture here, all right, so our extreme value theorem, which states that if f is continuous on a closed interval, then it has a min and a max on that interval, okay? So it tells us there is an existence that it has an existence of, it's called an existence theorem, okay? Because it tells us that there is an existence of the max and min values, and it just doesn't tell us how to find them. It just says that, okay, we have them, all right? And as you work on the homework on this, just understand that generally convention says that your local mins and maxes or your relative mins and maxes are going to occur on the interior points of your interval, all right? And the absolute max and mins can occur, they don't have to, but they can occur at the ends. In other words, you're not going to have a relative max or a min at an endpoint. That's reserved for your absolutes, all right? Okay? And if you think about it, it can't be that, it has to be absolute because we're closing it off. Relatives would be, because absolute says you can't have anything anything's not ever going to be larger than that value or smaller than that value. Whereas relative max and mins or local max and mins are just kind of happening at each of those points up there. So this is an example of where we have an absolute max occurring here within the middle, right? We have our absolute max here, because that's the highest point that this is really going to ever be. We have an absolute min here, that's the smallest value on the interval. Okay, and then you have local max and mins at those other places. All right, I just wanted to kind of clarify that a little bit. Your absolutes can occur at the endpoint on a closed interval. If you don't have a closed interval, then you don't have an absolute max or min. Right? Well, it's not going to be an absolute at the endpoint, I should say. Right? Okay. What else do I want to say? I wanted to work one more example from our relative max and mins, our extrema. And I'm choosing this problem because I wanted to choose this problem. Suppose that the population in thousands of a certain kind of an insect after 10 months is given by the following formula. That P of T is equal to 3T plus sine 4T plus 100. I want to know what the max and min population is for the first 4 months. So I am looking at a closed interval, all right? My closed interval in this case is from 0 to 4 months, right? For time. Now, what we learned yesterday was that in order to find our max and min, we're going to take the derivative of this function. So that's the first thing I'm going to do. So P prime is going to end up being the derivative of 3T is what? 3. Plus the derivative of sine 4T, so there is, what's the derivative of sine 4T? 4 cosine 4T And the derivative when 100 is just 0, so that's the derivative we have going on right there. Yeah? Now the next thing we do is we set the derivative equal to 0 and solve. So I would have 4 cosine 4t is equal to -3. Divide both sides by 4. I get cosine of 4t is equal to -3/4. In essence, I'm taking the inverse cosine of both sides, right? Because the cosine of the cosine times the inverse cosine gives me the argument back, doesn't it? All right. So in other words, 4t would be equal to, I'm writing this a little bit different than I have in the past. So we're looking at the inverse cosine of -3/4. So y'all get your calculators out and tell me what is, and by the way, this is a calculator problem, is it not? Okay, we're going to be in radians. And one thing I want to point out to you is when we are looking at cosine, what quadrants is cosine? In which quadrants is cosine negative? 2 and 3. 2 and 3. Cosine's negative and 2 and 3. When you take the inverse cosine in your calculator, where does it return a value? No, it's not 1 and 4. Sine is 1 and 4, tangent is 1 and 4.
And 1 is 6.
1 and 2 is where it's going to return values in 1 and 2. So Jonathan, when you took the cosine, inverse cosine of -3/4, because I'm assuming you did it already, right? All right, what'd you get to 4 decimal places?
2.4189.
All right, so that gave me the value in the first quadrant. Okay, and I now need the value in the third quadrant. How am I going to find that? Not yet. In other words, I have 2 angles that I should have here, right? The calculator only gave me 1. And oh, okay. What's that? Tell me what that gets you. Do it. Because if you're doing this at home, that's what you would do, right? What do you get when you do that?
3.864.
And what did you do?
What you said, the 2 minus that.
And you got what?
3.864.
Yep, that would be right. 3.864. Because that would give you the value in the third quadrant, wouldn't it? Because what is pi? 3.14. So at least you're in the third quadrant, right? All right. 3.6. Whatever that says. 3.68643. Okay. Now, we can keep going on forever, but we don't really need to right now, right? This is periodic. Now, this is equal to 4t, correct? So now what is t? All right. Okay, so that's this one. Right? That was the 3 divided by 4, right? 3 point something. What's the 2.4189 divided by 4?
0.6047.
Right? Okay. We've got two angles for what we need. Now, all I did was find out where, what the zeros were for the derivative, correct? And I would need to then plug them back in, right? How do we go about finding the max and the min? Well, we would take our function and evaluate it at 0 and 4, because those are the endpoints, correct? Along with the values in between, our critical values, correct? Yes, all right. So 0.6047, 0.9661. I'm gonna leave that like that for just a minute, and I want y'all to, I am gonna do this because it's calculator problem, so to speak, right here. Let's go to Desmos. And let's put that function in. P of x is equal to 3 plus cosine of, no, our original function, I'm sorry. It was 3t, beg your pardon, 3x plus sine of 4x plus 100. And I'm going to adjust my window here so that I can see this. Go from okay, so that's my function. I just zoomed in on it, all right? And I want to know what these values are, so I'm going to look at my table of values here. If I evaluate my function at particular numbers, I can do it using a table of values, correct? All right, so on the left, I have 0. The next point that I would have moving to the right would have to be that angle that we found, which was 0.6047. Okay, and then I have the next angle in there, which we said was 0.9961. Correct?
0.9.
All right, and so I still got to go along. So right now I'm only kind of in this area right here, aren't I? Right now I'm only at these 3 dots that are showing up. I need to keep going until I get all the way over here at 4, don't I? I've got to keep finding critical values, right? Because we know that on our sine functions or our trig functions, we can keep adding angles, can't we? How am I going to find the next angle past 0.6047? Could I not add pi over 2? Right? Plus pi over 2. What does that give me? 107? Yep. Still not there. I'm going to keep adding. Right? Are y'all doing this too?
What are we,
So I'm gonna add, I'm gonna add the angles. Remember the other day when we were adding, we don't know how many more to keep going here. 7. I'm gonna add. Where am I at on that? I'm at that next point here. And so if I'm here, this dot that I have right here, I just kept it all in numbers rather than seeing what the decimal value was, what it was. But let me back up for just a second. So we know that we had endpoints here, and let me enter out of that and put 4. So I have the left endpoint here at 0 and the right endpoint here at 4, correct? Yeah? Okay, that was the time frame that we restricted it to. I solved for 1 revolution around, in essence, right, of my trig function. Okay, and that gave us these first 2 values here, the 0.6 and the 0.9. And now I've got obviously more points that are going to occur here in between. So I'm just going to keep adding to my value as I keep moving around the circle. All right, the decimal representation ended up being, so the next angle was 2.1, 2.5, 3.7, and we stop, don't we? Because 4 is the end point, right? Okay. So I have all of these points in here, and I could figure out from my table of values over here on the side, right, what is the largest value that we found? What's the max? All right, 111.9. 111.9, so we have a max occurring here. And what is the min?
0.
I'm glad y'all answered it that way. The max is 111.9, and it occurs when x is 3.7. The min value is 100, and it occurs when x is 0. All right, so watch the language right there if you're doing that on any of your homework problems. The max occurs at, right, or the maximum value of the function is 111.9, and it's occurring when x is equal to 3. So it's at that point right there, right? The minimum value of the function is 100. It occurs when x is equal to 0. Okay, so when you're thinking of max and min, just figure out, just watch whatever you're looking at for the question, all right? So when we solve this together, I could have put in here that, how did we solve these the other day? Where we know that this value, the 2.149 you all gave me off your calculator, plus 2 pi n, and this other value plus 2 pi n, correct? Then if you divide everything in there by 4, you would end up with our values that we had, but I also have to divide my 2 pi n by 4, which is how I got pi n over 2. Tell me what those numbers were again. What was the first one? 0.6047 plus pi n over 2. That's how I was using that number. and 0.9661 plus pi n over 2. So if all I want to know is what the ultimate max and min is, and I'm going to evaluate the function, I didn't really take the time to find out what the decimal representation was of those values, but I certainly could have, couldn't I? And I could keep finding what these values were as long as I found values that were between 0 and 4. So every one of these numbers right here has to be between 0 and 4. Okay? And that's straight using your calculator to find those values. All right?
And then you just plug those t values.
Into the original function. So we did, what did we do? 1, 2, 3, 4, 5. I did that a total of 3 more times here. They end up being what, 2.1755, 2.5369, 3.7463. So this is the first number, right? And then I'm going to add pi over 2 to it. And that gives me the 2.17. Then I start with 0.96 and I add pi over 2 and I get 2.5. Then I'm not quite there yet, so I do 0.6 adding pi, so 2n, n is 2 now, right? Because I've already gone 1n, so I'm now at 2n. I'm going around again. Okay?
So the reason that we're adding all that is since the first 2 values that we had was just like short of being 1 be the ones that would lead up to 2, somewhere around 2, somewhere around 3. Or as well.
So with a trig equation, we only solved for the first 2 examples, or the first 2 problems, right? Or the first 2 answers, I suppose. And we can keep on going, but it's cyclical or it's periodic, right? So all we have to do is keep adding pi n over 2 each time I encounter that number, right? Those are coterminal angles. And so I'm only at 0.6 and 0.96 so far on this interval between 0 and 4. So I now need to go to the next coterminal angle with coterminal angle of 0.6. I find that by adding pi over 2 or 1 pi over 2. And then I add 1 pi over 2 to the 9.96. So I now have the second set, right? Those are the first 2 we solved for. These are the second 2 we're solving for. Can you see that? So those are the first 2 we solved for. This is plus pi n over 2. And then I only needed that one right there, didn't I? Because that was the end of the interval that I was interested in. Trig, right? That's how we solve trig equations. Remember that? Yeah? Well, you gotta remember them, so we're gonna keep practicing them. I know, we forgot, but at least you only had it 5 weeks ago and not a year ago, right? You did only have it about 5 weeks ago, right? Okay, that was why I wanted to show you that problem, because you have to keep remembering your trig and how you solve trig.
How do you know to stop going with those? Like you have those 3 that you.
So my interval, we were only interested in the first 4 months. So I was only looking for values between 0 and 4. So my x values only needed to be between 0 and 4.
So if you did the point, what is that, 9661 plus the 2 pi over 2, that would put you outside of zero.
Yep. Okay? Okay. Questions on that? No? Okay. What we're gonna cover now is the mean value theorem. Well, actually, we're gonna cover Rolle's theorem first. Keep in mind, or I want you to keep in mind, as we look at both of these theorems that we're talking about in this section, these theorems are basically used to prove other theorems. We won't, in essence, be using them to find very much, but that's why we're looking at them. So Rolle's theorem says that suppose f of x is a function that satisfies all three of these conditions. First off, that the function itself is on a closed interval from a to b. That the function is differentiable on the open interval from a to b. And the value of the function at a is equal to the value of the function at b. So let's suppose that all three of those things are true. If that's the case, then Rolle's theorem says that there exists some number c in between a and b. So we have some number c here in between a and b, such that the derivative at c is 0. That's all Rolle's theorem says. F is continuous and closed on the interval. All right. So Rolle's theorem is just saying that if f is continuous and differentiable, and f of a is equal to f of b, then there's got to be at least one value in between a and b where the function has a horizontal tangent, where the derivative is 0. That's what Rolle's theorem says. That's the picture on the left. Rolle's theorem is pictured on the left. The relative max. If f is continuous on a and b and differentiable on a and b. Now the second picture over here is just saying that if we drop that second requirement and we don't require the function to be differentiable, okay, then you still have a critical value, but you don't know if it's horizontal. Rolle's theorem is saying that you have a critical value that is differentiable at that point. That's all it says. You can see the difference in these two pictures, right? We have a closed function. We have a function that's on a closed interval on the picture on the right. But is the function differentiable at c? Because it's got a point up there, right? So Rolle's theorem says it has to be differentiable at c. That's how come the left picture is a image representing Rolle's theorem. Keep in mind that this is just a way to prove other formulas. So we're just discussing, it's a lot like, I would say that the theorems that we're going to look at today were a lot like the intermediate value theorem that we talked about in continuity, where we said that if it met certain requirements, then we were guaranteed that there might be, or we were guaranteed that there was going to be a solution between these two numbers because one number was positive and one number was negative. Do you remember that in the intermediate value theorem? Don't aren't shaking your heads at all. You remember anything like that? Vaguely intermediate value theorem? Just shake your heads, yes. Good, good. That's what today's lesson is gonna be is gonna remind you of. All right, let's put it into practice here. Using and applying Rolle's theorem. We want to find the two x-intercepts of the function and show that the derivative is equal to 0 at some point between these two points. In other words, we're just basically walking through and showing that Rolle's theorem does work. Okay, so what type of a function? What type of a function have we got here? If you had to classify that function, what kind of a function would it be? Polynomial, right? All right, and polynomial functions are continuous, correct? Okay, so that's good. Now, let's take this and let's first find the x-intercepts of the function. So when we set that equal to 0 and solve, this factors into x plus 1, x minus 1, x minus 2. So the x-intercepts are between, or there's two x-intercepts at 1 and positive 2. Okay. Now, Rolle's theorem said that, let me kind of sketch what we're looking at here. We have a quadratic function and it's passing through the points 1 and 2, correct? Something like that. It's positive, I know that, okay? Rolle's theorem said that if f of A is equal to f of B, and in this case they are, the function at 1 is 0 and the function at 2 is 0, correct? Because those are x-intercepts. All right. We also know that the function is continuous. If that's the case, then we should see that the derivative is some value that falls in between. That's all it says, right? That there was a C that fell in between A and B. All right. So the next thing we want to look at then is, let's take the derivative of our polynomial function f, which is 2x minus 3. Set that equal to 0. Solve it. And all we found is that here is the number 3/2. That is, in fact, where the derivative is equal to 0. And it is falling in between our 1 and 2. That's all Rolle's theorem says. And that's how we showed it. Rolle's theorem states that when the function's conditions are satisfied and met, then there's got to be at least one point between A and B where the derivative is 0. Again, it's like the intermediate value theorem. All right, that's all it says. So we showed it. It meets Rolle's theorem. All right, now let's look at another one then. We have the function x to the 4th minus 2x squared. And I want to know, what are those C values that occur in the interval between negative and positive 2? So if we apply Rolle's theorem here, we want to know, is the function continuous? Is f of x continuous? Yes, and is y? Why is it continuous? Because it's a polynomial, all transcendentals, right? So logs, exponents, rationals are even continuous where they are defined, where their domain is defined, all right? They're all continuous on their domains, all right? So yes, it is continuous. All right. And the next thing that we want to know is f differentiable on that interval? Well, it's a polynomial, and if it's continuous, then it would be differentiable. Okay, so yes. Now, the last thing we're trying to use Rolle's theorem here is we want to know, does f of a equal f of b? Now that I don't know just yet. But my interval is defined as negative to positive 2. So that's A and that's B. So let's substitute in f of negative 2 and f of positive 2 into the polynomial. So negative 2 to the 4th minus 2 times negative 2 squared. It's going to give you 8. And 2 to the 4th minus 2 times 2 squared would have to be 8 as well. Are you checking me? Smart. Yeah, it's 8. 8 and 8. 2 to the 4th is 16 minus 4 times 2 is 8. So 16 minus 8 is 8. So we just met all of those criteria, right? So Rolle's theorem says if all 3 of those things are met, then you've got to have somewhere on that interval zeros of your derivative, right? You've got to have your horizontal lines. So now let's come through and find out, well, where is that occurring? Where are those horizontal tangents at? Or in other words, where is the derivative equal to 0? So the derivative of the function is 4x cubed minus 4x. I can factor 4x out, x squared minus 1. 4x is equal to 0, x squared minus 1 is equal to 0. So x is equal to 0 and positive and negative 1. These are the C values that were guaranteed by Rolle's theorem. Those numbers all fall within that interval, don't they? That's all Rolle's theorem says. And that's how you show it, okay? All right. Following Rolle's theorem, we have the mean value theorem. Okay. So we're kind of building on Rolle's theorem here. This image, so write down the theorem, but write down that image on the left. The mean value theorem says that if f is continuous on a closed interval and differentiable on an open interval, which is just what Rolle's theorem said, and we know from Rolle's theorem that there exists some number c inside of it. The mean value theorem says that the derivative at that point C is gonna be equal to, what is this thing on the right? What is this thing? Slope of what?
A to B.
It's the slope of the secant line, right? It's the slope of a secant line. It is slope, and in this particular case, it's the secant line. So if you look at the picture here, the mean value theorem is basically saying that the slope of my secant line is going to be equal to the slope of the tangent line at C. That's the mean value theorem. Okay? And I think it's pretty clear to be able to at least see. Do you all agree with that those two would have to be the same slopes? Because they're parallel, right? And they're parallel at that point C. Now the picture on the left, by the way, the mean value theorem is referring to what we would say in statistics, right? The average or the mean. Okay, the mean value theorem refers to the average rate of change for your secant. So if we were to continuously have, it's the average of that change of the secant line. Now over here, what I want you to just understand, it says a corollary to the mean value theorem is that the graphs of functions with identical derivatives, the graphs of functions with identical derivatives on an interval, they differ by only a vertical shift. The reason I think this is important for you to see, whether I think you're going to remember this in 2 weeks or not, I'm not sure. But when we do integrals, this is important to understand that integrals are the undoing of derivatives. So if a derivative is only on a particular interval here, are only separated by a vertical shift, we're going to see that concept again when we talk about integration. Okay. Okay. So what we want to know and understand out of this mean value theorem is that the derivative at C is going to be equal to the secant, the slope of the secant from A to B. Okay? All right. So for this question here, I want to know, well, what is that number C? What is the number C that satisfies the conclusion? And this is the polynomial that we're going to look at. So we're talking about the mean value theorem states that the derivative at C is equal to the slope of the secant on the interval from A to B. So the slope of the secant line can be found by taking the function at, I'm going to use B, so f of 2 minus f of -1 divided by 2 minus a -1. Well, what's the value of the function at 2? What's the value of the function at -1? Come on, middle math here. What's the value of the function at 1? At -1, it was 2. So 2 plus, this would be plus, 2 plus 1 has to be 3 in the denominator. Or in other words, 14 minus 2 is 12 divided by 3 is 4. And the derivative of the function is 3x squared plus 4x minus 1. So the mean value theorem says the value of the derivative at c. So I'm going to just rewrite this so it's a little clear. You don't have to do this, but this is what I'm going to do. In other words, if the derivative at c, let's say that the derivative of c is 3c squared plus 4c minus 1, the derivative at c has to be equal to the secant on the interval from a to b, right? Or the slope of the secant. So in other words, that's got to be equal to 4. Wasn't that the slope of the secant from a to b? Okay. So now I have a quadratic equation here that I'm solving for c, right? So this would be 3c squared plus 4c minus 5 is equal to 0. This doesn't factor. So I would say c is equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And when you do that in your calculator, you find that we should get 2 answers, shouldn't we? So we should have 0.786 and negative 2.119. The interval we're interested in, however, is from -1 to +2. So this answer here is not on that interval. So the mean value theorem says that when x is equal to 0.786, right, the slope of the derivative has to be 4, because the slope of the secant is also 4, right? The mean value theorem in this particular case is I'm only looking for what value, what's the value of c? What c fell on that interval that caused the slope of the derivative to be the same as the slope of the secant? That's all we were looking for. What number between a and b causes the slope of the secant to be the same as the slope of the derivative? All right, let's try that again. So here I've got the function 5 minus 4 over x on the interval from 1 to 4. So if I'm using the mean value theorem, I'm going to come in here and I'm going to find out what is the slope of the secant. It's the value of the function at 4 minus the value of the function at 1 all over 4 minus 1. What's the value of the function at 4?
4.
And the value at 1 is 1. And 4 minus 1. So that's just 1, right? Okay. Let's find the derivative. We're looking for 5 minus 4x to the negative first. So the derivative is going to be positive 4x to the negative 2, or 4 over x squared. So the mean value theorem says, what value at C? What's the value of C for the derivative, which would be 4 over C squared, when the slope of the secant is 1? So 4 is equal to C squared, or plus or minus 2 is equal to C. But I only need the positive value for 2. Because it's on that interval from 1 to 4. Okay? Mean value theorem is fairly straightforward. Questions on that? No? Okay. Well, we're just chugging along here, aren't we? Need to get up, go stretch your legs, do some jumping jacks, something, speak maybe? Yeah? No? How are no fine today? This I did. Yeah, did I have this posted?
I didn't see.
That's good.
Well, because I thought we were doing the first derivative test.
No, I moved it.
You moved it?
Yeah, I moved it.
No.
No, I guess I didn't post it. I didn't. With the intention of it being posted. Because there was 2, oh, no, you saw 2, but you didn't see the third one, did you? There's not 3 up there, right?
There's only 2.
Well, I can post it right now if you want to go print it out. Yeah? Yeah? I'm not gonna do it if y'all aren't gonna speak.
Yes.
Huh? Oh, okay. Like, have a conversation?
All my brain
But
power
it's
is
more
going-
exciting when people are speaking to you.
Using all my brain power to think about. what-
That's why we need a break. That row right there, they need to speak. That one right there, they just stare. All right, everybody else that's in here has to stand up. You just have to stand up. Then if you're gonna do something, like go, walk, do something. Get your brains going. Before I seriously make you do wall sits, burpees, something. Yeah. Give you my Pilates. You die.
I don't mind working out.
You need it right now. Where's your derivative test? See, it's right there, Sam.
Alright, so it is. Oh, you're.
I mean, I did it. I just didn't upload it.
Yeah.
I'll be sitting for that.
Hey, y'all are just standing, you're not doing anything. What kind of homework have you got this weekend? Don't know?
I'm doing something. My brain is.
Did she go over the?
Pretty like that.
The number 8 from the kids?
Pretty nice. I got two as a quarterback.
Now it's there.
What?
Stuff, yeah. Okay,
Like how, after the break, you want to do
so we have to solve I already forgot how to do this. It's been one day, or like 2 days.
I missed something last one.
Like for, intro.
Yeah.
It's honestly, just like a taco, but it's like, it's like the latter, like 40, 50 minutes.
With,
No, there wasn't. You're fine, that'll be hard. Yeah, it was like ethics of being.
Boring.
Yeah.
I forgot to set my alarm.
Yes.
Alright.
Yeah, me too.
Yeah.
Which, I installed this,
But
like.
Yeah, they're all
anything behind the background TV, so it'll react to what's next to the screen and display that. I forgot what, and I'm like, so I want to use it, because I spent so much on it, so much time.
Yeah.
So I decided to start a little game or something like that last night, and I put that all on episode, and
You like
I
it?
don't like it.
I enjoyed the first episode.
Did you watch more than one episode? The first one's kind of boring.
All right, what happened on the first one?
Oh, it's on number
The first
7?
one is basically just introducing.
No. Yeah. It's like the game in the
They're throwing the.
Yeah.
Oh, that was dumb.
And he gives them like
I
100,000.
think I did watch more.
Actually, I think the second one was the most boring.
Oh, yeah, no, I remember that.
It was like they all went home.
What formula did you like?
Oh, wait, did you watch it?
No, I only watched.
That's why you wanna say.
I'm sorry.
No, as far as I know, they did the
So-
red light, green light, a bunch of people die, and then it's like, okay.
That was fun.
Now-
I used to find that.
See, and that's when I was like, I'm not
X
watching
squared.
Yeah, the
square, right?
The deaths.
We just kind
Oh.
of compared to
Oh, okay.
you solve S using the Pythagorean theorem.
like,
we watched it from my
So-
son
This one-
suggested it. We're not letting
Yeah.
him suggest
So
it
you
anymore.
get 2x.
I've tried suggesting shows with my family, but they're always like, my mom's the kind of type where it's like she'll find a show and then she'll just rewatch that same show over and over again. Like, I think she's watched the entire Supernatural like 5 or 6 times over. It's like
No.
14 seasons total.
Oh, wow.
Yeah, so it's like, hey, here's this really cool show that I just watched.
No, you're walking this way.
Yeah.
'Cause I was trying to get her to watch Breaking Bad because I think she'd really like it.
Uh-huh.
Right.
Nah, I'm just gonna keep watching the shows.
Oh. Yeah.
That's so good.
I don't know, we're in a rut.
Yeah.
My daughter let us
negative
know that,
value for,
Stranger Things
For
trailer
DYDC.
finally came out,
Oh,
so
really?
maybe that'll.
I only watched it first.
I watched all of it. I watched all of it. I really
It's
liked
getting
it.
kind of dumb, but at least it was something we could watch besides,
The frick.
what is it that
Wait,
we're,
the one that the,
it's a game show.
So
Not the Price is Right, it feels like it, though.
2x.
I don't know, it's on the.
Never been here.
There's only so much I can watch of it, so.
Why?
All right, y'all can't talk forever, please sit down, my gosh.
oh no.
Why didn't it do D5 or D8?
Can we go over the Reddit rates again?
I told my son, I said that, I said something like that, you know, or whatever, and my son's like, yeah, I was talking.
I do not.
It's like, All right,
I was gonna ask you something.
so what we're gonna do for the remainder of the period for the next 45 minutes is we'll talk about the first derivative test, which is pretty important. So you wanna make sure that you're looking at it. And there's a Desmos lesson that needs to be completed over this, all right? Tonight, all right? I want you to look at it. It's already up, okay? It's only got 17 questions on it. I want you to get as far into it as you can, all right? I'd like to see that you know how to do it,
What?
okay?
One of the ones where we have to write something out.
I'd like to see, no,
Okay.
you don't have to submit anything. I just want to see that you've done it. One's a card sort, all right? Try to work on it a little, all right? I haven't decided what to do with that one yet. I would just highly suggest that you finish it at your own time.
Yeah.
Okay, because it gives you good opportunities to practice those problems without it showing up as a multiple choice.
Oh, the rest of them are on.
You know what I mean? Because they come from the homework. They're similar to the homework. But the homework problems are gonna give you the choices as opposed to you having to think about the choices. All right, so no, I would say that the Desmos lesson that we were working on yesterday, please just try to complete that for your own benefit. All right, the one that I put up today, I would like for you to finish it. I'm just kind of saying that I realize you have other homework to do, but you need to practice on this and I need you to be practicing on it. All right,
So the rest of the one that we did yesterday is the one.
I unlocked it, I think when we were in here.
How many the Pearson ones are we gonna have?
So, you know which one you like to do?
How many homework lessons?
Yeah, how many the
What?
homework?
PYT
assignments for
negatives.
Pearson? The my math lab.
For the semester?
Oh, you just did twice.
No, just for this week.
Oh, how many lessons are we covering?
Are we covering the other ones tomorrow?
Yeah.
Got it.
One,
I saw one.
Two,
Yesterday. so-
3, 4, I mean 5.
Yeah, the one from
Five.
yesterday wasn't up yesterday, but I think this morning it was up.
Right, I realized that. I got it put up last night.
I forgot.
Those are short. The mean value theorem is short. I mean, you saw how long it takes to kind of work those problems. What's the other one? The max and min. I don't know how many that one has in it.
I was like,
That's right, that's only all right.
How much I have. This week.
So just try to get the Zoom, the Desmos lesson completed as best you can, because I would like to see how well you're doing on it, all right? Okay, let's move on. The derivative. The first derivative test is what we're gonna talk about today. We talk about the second derivative test tomorrow, and then we do our curve sketching next week, all right? But we're kind of actually doing it the whole time. This states that we're kind of defining formally where a function is increasing and decreasing. We already know this because we've been practicing this for a long time now, it feels like. So when we have a function that's defined on an interval, we say that it is increasing on that interval if f of x2 is greater than f of x1, when x1 and x2 are in that interval. In other words, all of that math speak is showing you in the picture right down there. We know when the function is increasing and decreasing, right? When the value of the function is getting larger, as x is getting larger, right? Then the function would be increasing. Okay. We can test for increasing and decreasing functions this way. So this theorem states that when f is a function, it's continuous on a closed interval and differentiable on an open interval, then the derivative, if the derivative is greater than 0, the function is increasing on that interval. If the derivative is less than 0 on that interval, then it's decreasing. And when the derivative is 0, then it's constant. All right, so putting it into words, this is the same thing we've been looking at repeatedly, okay? Now we're gonna kind of do it a little more formally with this next problem. So for this first problem, I want to do two things. I want to know where the function is increasing and decreasing graphically. In other words, tell me based off the graph, where is the function increasing? Okay, so it's gonna be increasing from negative infinity to -2. And then from 2 to infinity, right? Okay, that was occurring up until that point. And it also started occurring again from that minimum point to the right. Any place in between, we would say the function is decreasing, correct? All right, now to show this analytically, or in other words, I want to show it algebraically, I am going to find the derivative. Now let's just write down really fast. We are increasing on the interval from negative infinity to -2, and then again from 2 to infinity. We are decreasing on the interval from negative to +2. And when you put those into Desmos, do it just like I did right there, okay? I'm surrounding it with parentheses, but I'm not putting a space or a comma in between those two sets. So how could I show this analytically? We can see it visually, but how do I do it analytically? Well, we're going to take the derivative of the function. So the function h of x is equal to 1/4 x cubed minus 3x. So I pulled the 4 out from the denominator, wrote it as a 1/4, or I moved the x cubed, I should say, out of the numerator. So the derivative now of this would be 3/4 x squared minus 3. Correct? That's the derivative. Now, we're going to take our derivative, we're going to set it equal to 0, and we're going to solve the derivative. So 3/4 x squared is equal to 3. X squared would have to be equal to 4. Therefore, x is equal to plus and minus 2. Visually, we remember that that is the case, right? Because where the derivative is equal to 0, the tangent to the function has to be horizontal at negative and +2, right? Okay, so what we're going to take now from this derivative is, I'm going to take the derivative. Let's put down our numbers here. So I have -2 and +2, which are represented from the x-axis. That's where the derivative crosses the x-axis. What I want to know is, I want to test some points around those critical values of the derivative. Remember, those are critical values. So I'm going to choose a value to the left of -2 and plug it into the derivative. And what do we get?
We're just looking for the positive or
Uh-huh.
left of -2 is positive.
Okay. So I chose -3, and in fact, it is positive of the derivative. And let's choose a value in between. Let's choose 0. What is the value of the derivative at 0? Negative. What's the value of the derivative at +3? Positive, right? So the function itself is increasing when the derivative is positive. The function is decreasing when the derivative is negative. And the function is increasing when it is positive. So what we're going to kind of expand here is, let's make a conclusion about the function, not the derivative, but I'm making a conclusion about the function. In other words, we can see if I don't have the graph in front of me, I can figure out by taking the derivative that the function itself is going to be increasing from -infinity to -2, and again from 2 to infinity, based on my little chart I'm making. And the function is decreasing from negative to +2. So now we're going to kind of start building this idea. Even though I could put the function in the graphing calculator and see it, I can prove it analytically through the derivative, which is what you're going to do. Let's look at another example here then. Here we have g of x is equal to x squared over 2x minus 1. The function is increasing until we get here. The function again would be increasing as we move off in that direction. You can't really see this graph here, but this does come above the x-axis. We'll see that in just a second. And it's decreasing in between, right? We have an asymptote in there, don't we, though? So we know from the graph, if you could zoom in on it, that the function is increasing on the interval from -infinity to 0. And again, from 1 to infinity. And it's decreasing between 0 and 1/2. So that's up to the left side of that asymptote. And it's decreasing again on the right side from 1/2 to 1. Okay. Now, how do we show this analytically? So we want to come down here. Let's take our derivative. The function is x squared over 2x minus 1. And already we know that where does the function not exist? Right? There is an asymptote where x is equal to +1/2. So the function would obviously not be differentiable at 1/2, right? But 1/2 is a critical value. So we want to keep that in mind. Now let's take the derivative of this function. So I'm going to just use the quotient rule on this one. I'm going to let the numerator be f. And the derivative of f would have to be 2x. The denominator g is 2x minus 1, and therefore its derivative would just be 2. So G prime says that this is the low D high, high D low over low squared, right? All right, so low being the denominator. So low would be 2x minus 1. D high would be the derivative of the numerator minus high x squared D low all over low squared, 2x minus 1 squared. So make sure that your numerator looks like this. We have 2x times 2x minus 1 minus 2 times x squared all over our denominator. So when I simplify this, we've got 4x squared minus 2x minus 2x squared over the denominator. Or in other words, 2x squared minus 2x over the denominator. That's the derivative. So we want to find out where the derivative is equal to 0 now. So I'm going to set it equal to 0. And I find that 2x squared minus 2x is equal to 0. Let's factor a 2x out of that. So 2x is equal to 0, x minus 1 is equal to 0. X would be equal to 0 and positive 1. But don't forget, just like above, that the derivative does not exist when x is equal to 1/2. So these three values, 1/2, 0, and 1, are the critical values that we need to evaluate at, okay? Okay, so we're gonna draw our number line kind of like we did, and we're gonna test our values around that. So I have 0, 1/2, and 1. And I'm gonna try to make note, I'm gonna remember that that 1/2 is an asymptote. So we're going to evaluate the derivative around these points. So I want to know what the value of the derivative is to the left and right. So get your numbers out. Let's try this. So to the left of 0, what's the value of the derivative? Okay, so to the left of the 0, to the left of 0, the derivative is positive. What about from 0 to 1/2? Are you sure? What number did you choose?
One was negative.
Okay. All right, how about to the, in between 1/2 and 1?
Also negative.
And how about to the right of 1? Okay. So when the derivative is positive, the function is increasing. When the derivative is negative, the function is decreasing. So we can state now that the function is increasing on the interval from negative infinity to 0, and again from 1 to infinity, and it's decreasing from 0 to 1/2, and again from 1/2 to 1. Just because we're negative on both sides of 1/2 doesn't mean that I go from 0 to 1 and say that it's increasing, right? Or decreasing, right? I can't make it from 0 to 1. I can't say the whole thing is decreasing because we have that asymptote that's occurring right there in the middle. Okay. You kind of see where this is going? Because we're going to be sketching these things based on this information. In other words, we're not starting with the graph. All right. Now, something to just understand before we practice this. We have this term where we're talking about monotonic. A function is strictly monotonic on an interval when it is either increasing on either side or decreasing on either side. Just kind of look at the differences of what you have right there. What I want to kind of show you is we can be increasing, slide over, and increasing again. I think that you drew something that looked like this yesterday when you were sketching those, now that I'm thinking about it, didn't you? I remember Jonathan sketched one like that, pretty sure. You drew something that looked like that when we were sketching our stuff on Desmos. So you can have like a little pause, maybe I should call that, or you could have a longer pause, all right? Both of those are showing that you're increasing, okay? So what if we took this idea here and I want to, based on these characteristics, I want to draw a function that would satisfy these characteristics, all right? So starting off, we have that we have a continuous function. And we know that the derivative of the function is positive from negative infinity to 0, from 4 to 6, and from 6 to 8. We know that at 0, the function is undefined. We know that at 4 and 6, the function is equal to 0. So we have 2 points here that are interesting to us. And then we also know where the function is negative. Okay. So what we want to do, taking that information that you see right there, we have our graph that we can kind of start at. We've got our x-axis here. And I know that at, let's see, we'll go with, start at -4, 3, 2, 1, 0. Okay. And I've got values from -4 to +8. I know that the derivative at 4 and at 6 is 0. Right? I know that the derivative at 4 and 6 is 0. And so when the derivative is 0, what do we have happening to the function? Okay, so we have a max or a min, right? All right, so I have something happening here. I have either a max or a min. And then at 6, I have the same thing. Max or a min. It's undefined at 0. So here we have, it's a continuous function. So we have either a corner or a cusp because it's continuous. From negative infinity to 0, we are increasing. From 4 to 6, we are increasing. From 6 to infinity, we are increasing. And we are decreasing in between, from 0 to 4. Okay, so a cusp, what does a cusp look like? A cusp or a corner looks something like that, doesn't it? We are decreasing until we get to 4. We're increasing, and then we are increasing again, right? It doesn't necessarily mean that we have a max or a min. It could also talk about it being a horizontal, right? The tangent could be horizontal at that point as well, if it's 0. So we might have something that looks like we're increasing, increasing again. Kind of. Is that what y'all drew? Did you draw anything? Okay. So far all we've talked about is increasing versus decreasing. The first derivative test, it's a little bit more specific. And the first derivative test says if the derivative changes from positive to negative at that value, the critical value, right? If it goes from, I don't know what I just said, if it goes from negative to positive, if it's going from negative to positive, you have a minimum. If it's going from positive to negative, you have a maximum. And both of these would be relative or local. So we're going to take what we just talked about from increasing and decreasing and build on it to be able to identify where you might have a max or a min. So we're going to look at this function right here, 1/2 x minus sine x. And we want to find the relative extrema, which would be finding the local max or min. So the first thing we want to do is take the derivative of the function. F prime of x is equal to 1/2 minus cosine x is equal to 0. And we're only interested in the values between 0 and 2 pi. So I'm going to add cosine to the right. I'm going to figure out what angles, when I take the cosine of them, do I get positive 1/2? And that occurs at pi over 3 and 5 pi over 3. Those are the critical values, aren't they? Is there anywhere where this function would be undefined, by the way? Is there anywhere where this function would, the derivative would not exist? No, right? When you think about undefined, you would think about the variable being maybe in the denominator. So asymptotes, you would think about under a radical, under a square root sign, right? Something like that, or a piecewise function, but we don't have that. So let's take this and let's test around our critical values. So we have pi over 3 and 5 pi over 3. And we're going to test the derivative. That's your job. Test the derivative to the left and to the right of pi and 5 pi over 3. So to the left of pi over 3, what is going on with the function? What's the value of the derivative? Is it positive or negative? It's negative. What's the value of the derivative in between? What's the value of the derivative to the right? Negative? What did you choose? To the right of 5 pi over 3? Aren't I looking for a number that's greater than 5 pi over 3?
2 pi.
Oh, yeah.
And it's positive?
Negative.
Negative. Thank you. Okay? So if the derivative is positive, is negative, positive, negative, then the function would be decreasing, increasing, and decreasing. And we can conclude then that when we go from, when the first derivative goes from decreasing to increasing, we have a max. No, we have a min, sorry. I don't know what I was thinking. We have a minimum value. When it goes from increasing to decreasing, we have a maximum value. Right? That's for the first derivative. It's going to identify for us where the max and the mins are. Okay? Let's look at another problem. X squared minus 4 raised to the 2/3. And do y'all, I would encourage you to look and to see whether or not a cubed root, fifth root, any odd root function. Do you know what a cubed root function looks like? Y'all remember what a cubed root function looks like? What's it look like? Cubed root function looks like this. It's sideways. It's continuous, right? As opposed to a square root function, which is only defined for positive values, right? So even root functions would only be defined for positive values. Odd root functions are in fact continuous. They all, and you can try, just play around. It can be really easy to graph a fifth root, a ninth root, an 11th root, and see what they look like. So you have a continuous function here, which is important to understand. All right. Now, what is the derivative of this function? So f prime would be, this is the chain rule, isn't it? Okay, so it would be 2/3 x squared minus 4 to the negative 1/3 times 2x. Very good. Okay. So I'm going to rewrite this because I'm trying to solve this. So I'm going to rewrite this so that it looks like 2 times 2x would be 4x in the numerator over 3 times x squared minus 4 to the 1/3 in the denominator. So the 3 here that's in the denominator goes with the negative 1/3 guy into the denominator. Okay,
Where would you? Is-
okay, so I'm going to set this equal to 0 and solve. So the numerator gives me the x-intercept. What does the denominator tell me? Right, so we would have the denominator 3 over x, or 3 times x squared minus 4 to the 1/3 is equal to 0. If I divide by 3 and raise both sides to the exponent, it gets rid of everything, doesn't it? In essence, we can, since it's set equal to 0, I can just pull out what was inside of the parentheses. X squared minus 4 is equal to 0. And just like Sam said, x is equal to positive and negative 2. These are asymptotes, right? This is where the derivative is undefined. Because it's asymptotes, it's just where the derivative would be undefined. This is where the derivative has an x-intercept. In other words, they're both critical values. So we're going to test those critical values at, we have a -2, a 0, and a +2. And I want to know what's happening around those values. So I just want to know where the function, I want to know what's happening. I want to know whether or not the function is increasing or decreasing in those areas. So at -2, what is it? To the left of -2. Decreasing? Mhm. About -2 to 0, what is it? What's next? What's next? Increasing. Okay. So let's put some of this together as we come to the end of this. Ultimately, when we get to curve sketching on Monday, we're curve sketching the function. So we're making conclusions now about the function. Fn is the function. I'm making conclusions about the function using the derivative. So I can conclude that the function is increasing on the interval from -2 to 0, 2 to infinity. I can conclude that the function is decreasing on the interval from -infinity to -2 and from 0 to 2. I can also conclude that what's happening and what was our, these are both undefined, right? All right. And let's look at C, what that looks like. What does that function look like in our calculators? Okay, we know that the derivative is undefined here, but the function itself was continuous, wasn't it? Now what we think? What does this function look like? Did you throw it into your calculators? It looks bouncy and it's a parabola. Oh, is it the one where it's got like a bat ears? I don't know. It's like gotta go down and then it's got a hump and then it goes up. Okay. All right. The function,
Okay, I had the third.
the function.
Oh,
It looks like that, right? Okay. All right, well, that would make sense then. So here, even though the derivative doesn't exist at -2, we still have a minimum value, don't we? And we can see that by the increasing, by decreasing and increasing, can't we? All right, so we would have a minimum here, we would have a maximum here, we would have a minimum here. That's because the function itself is continuous.
In this case, would both of the minimums be the absolute minimums?
I would say that they would be an absolute minimum. I'm trying to think. I'm pretty sure that if I'm thinking about the homework, that we drop absolute past the very first section. And we're really just, we just want to know where is there a max and where is there a min, kind of like how we always called the max and mins up until then. Yeah. All right, the last one we want to look at here. Okay, so we have our function, x to the 4th plus 1 over x squared. I want y'all to find the derivative of this function. This is what y'all are supposed to be practicing. Yeah, you can use it. Once you find the derivative, solve the derivative and find your critical values. So make sure that your derivative is 2x to the fourth minus 2 over x cubed, and then solve it.
So I know you get the same answer, but why would you go ahead and cancel out that?
What x?
You cancel out, well, x to the fifth turn into x to the fourth, 2x turns into 2, and x cubed just turns to, or x to the fourth turns to x to the third. Why did you do that? If you get the same answer if you leave it.
I just simplified it.
Would you have to do x cubed, so that equals 0?
I already know that there's an asymptote at 0, so the derivative doesn't exist at 0. But I can kind of pull that out and remember what's going on there. So -1, 0, and 1 are the critical values. What's happening to the derivative around those critical values?
To the left of the -1, it's negative. To the right of -1, it's positive. To the right of 0, it's negative. To the right of 1, it's positive.
Okay, very good. Now, what kind of conclusions can we make from that? About the function. Where is the function increasing?
-1 to 0.
Where is it decreasing?
Negative infinity. And 0 to
And where do I have relative extrema? Where? So what would I have at -1? I would have a minimum. Where would I have the next one? Over here at 1, I would have a minimum also. Do I have anything at 0? Because it's an asymptote, right? How would I find out what the point is where the minimum is located at? Plug it in where?
To the original function.
All right, so f of -1 equals whatever the value is, right? the function, because this minimum right here, this extrema, the local min and max occurs on the function. So I want to know what's the ordered pair, what's the point on the function, okay? All right, you understand what we're doing kind of with these? Because we're gonna expand this to the second derivative tomorrow. All right, the second derivative test. That's kind of why I want you to practice these just a little bit. All right? Spend 30 minutes, that's all I'm asking. 30 minutes working on this tonight, okay? All right, y'all have a great day. I'll see you tomorrow. Come with your running shoes on.
No, no, no.